Friends, family, YouTubers, lend me your ears and your eyes. Take a look at this and tell me what you think. Now just what exactly is going on here? To find out, just keep watching. If you're like most people, you probably had a really terrible maths teacher or even a series of really poor maths teachers. You know, just people who didn't have a love for mathematics or were poor at communicating. And the result is an entire portion of the population who are cut off from a source of beauty that would otherwise enrich their lives. Now, if you don't think this is a problem, then fair enough, I sympathise. But please try to imagine something that does enrich your life, like music or literature or art or plays, or it could be anything at all. And now just try and imagine what it would be like if you couldn't appreciate this thing. It's kind of sad, isn't it? So if you're one of those people who has never said, "That's beautiful," about something in mathematics, I'm going to try and change that today. I'm going to show you something that will make you think differently about prime numbers forever. Alright, I want you to think back to your childhood. How were prime numbers explained to you? Well, if you're anything like me, it was explained to you that a prime number is any number that is divisible by only 1 and itself, and by no other numbers. But does that really give you a sense of what they're all about? If you're anything like me, then the answer is no to that question. It really doesn't give you an intuitive sense of what they're all about. So over the years, I became a lot more familiar with prime numbers, even though I didn't have an intuitive grasp of what they were all about. I learnt that there was an infinite number of them. I learnt that they have a certain distribution. I learnt that they're the multiplicative building blocks of all numbers. But it wasn't really until 2012 when a software engineer named Brent introduced factorization diagrams that I really got what they were all about. And that's what I'd like to show you today. Let's start with a simple example first. Now let's say that you and a group of friends are trying to work out how to share a certain number of delicious morsels. I'll choose as my example the humble Tim Tam, which is a delicious chocolate-coated biscuit that we Australians love. It's as Australian as Vegemite. Okay, let's say we have 6 of these things. It's a nice non-prime number. And let's say you've just got one other friend. Then would you be able to evenly share them with your friend? Well, yeah, of course. The answer is that each of you would get 3 of the biscuits. Now, this also works for 3 friends. Each of you would get 2 biscuits. And it also works in the very boring case of 6 friends, where each of you would get 1 biscuit. And that pretty much exhausts the number of ways you can share 6 biscuits amongst more than one person. And now on to a very, very serious matter. Do any of you actually know how many biscuits are in a Tim Tam packet? Anyone? I'll just give you a moment. Alright, it's 11. And 11 is a prime number. And I can tell you that Arnott's Biscuits definitely do this on purpose. Because 11 biscuits is really hard to share out amongst the kinds of groups you would find in everyday life. You can only evenly divide it amongst 11 people, and each one of them will get 1 biscuit. So this is a good way to think about primes. Primes are those numbers which cannot be evenly shared amongst any group other than one of size 1, boring, or the prime number itself. And if the prime's large enough, you're never going to find a group that large. So I think Arnott's, what they're trying to do here is get you to just buy more packets of Tim Tams. So now we have to ask ourselves the question, how would we represent a prime number visually? Well, let's just start with a composite number first. We'll start with 6 again. And we can see that 6 can be arranged in a rectangle in 2 ways. you can either have 3 rows of 2, or you can have 2 rows of 3. So what I'd like to suggest to you is that this is actually a great little test for whether something is prime or not. See, if you can arrange a number in a rectangular shape where it doesn't have just one row or one column, then you have got a composite number for sure. And if you can't arrange it into a rectangle, no matter how hard you try, then it's prime. Now let's move on to Brent Yorgi's factorization diagrams. Now I think he had an ulterior motive in the design of his diagrams. I think he wanted you to be able to see that primes are the multiplicative building blocks of all numbers, and I'll show you how I think that's possible. But let's first ask ourselves the question, if we can't group a prime number into a rectangular shape, then how would we represent it visually? Well, Yorgi's solution, which I think works really quite nicely, is to evenly space the objects around a circle. So 7 will look like this, and 11 will look like this, 3 will look like this, and 2, I think a little counterintuitively, will look like this. Now Brent Yorgi actually had the genius idea of making his diagrams recursive. Now what do I mean by this? Well, I mean that we're going to have diagrams within diagrams within diagrams and so on, one for each prime factor. So to illustrate this idea, let's just take the number 6 again, and we know its factors are 3 and 2. So as a first step, we know that we're going to have 3 diagrams evenly spaced around the side of a circle. But what do we put in the sub-diagram? Well, that's pretty easy. We just put a diagram for the other prime factor, which is 2. And we end up with this. And we can continue this process as far as we want. We will have diagrams within diagrams within diagrams, depending on how many prime factors there are. So, as an example, let's take 30, which has factors 2 times 3 times 5. That means we're going to have a diagram that is 3 levels deep. Well, it ends up looking like this. I think this really nicely illustrates that prime numbers are the multiplicative building blocks of numbers. You may not know this, but each number has a unique prime factorization. So with that out of the way, now I can show you my software project. So while going for a jog one day, I suddenly had an epiphany that these diagrams would look really good if animated. So I thought, I'll just have a counter. Starts at 1 and goes as high as I wish to watch the animation for. And at each point, a new object comes in, and somehow the objects that are already on the page rearrange themselves to form the next prime factorization diagram. Well, you know, I was prepared for this to look a bit crap, but it ended up looking much better than I initially expected. So let's have a look at that now. Let's start at 1 and count up. There's 2, 3, 4, 5, a circle, 6, 7, another prime in a circle, 8, 9 looks really nice, 11, prime, another circle, 13, a circle, 17 will be a circle, as will 19. Another prime. "27 is beautiful. The next one like that is 81. We're coming up to a square number soon, 36. I think you'll find it's quite beautiful. Look at that recursive structure. Now let's speed up the animation a little, and I'll just let you soak it in for a while. If you'd like to play with this effect a little bit more, please go to seanseafried.org/effects/factor diagrams. I've put the URL at the bottom, and have a play around. Well, I hope you enjoyed that, and I do hope that you go to my site and have a play around with it. This is actually the second version of this video that I've made. The first one was heavily scripted, and in this one I tried to be a bit more ad-lib and just, use some rough bullet points in order to structure my talk and basically talk off the cuff. So if you preferred this version, I'd very much like to hear about it, either in the comments or through private correspondence. Thank you very much again for watching. I will see you again soon with something random that I happen to be interested in.